right? Can we write the equation for the speed relatively straightforward? Yeah, the speed of this particle is going to be equal to the square root of 3t squared minus 3 squared plus what? 2t minus 2 what? Squared, and it's the square root of that, right? So if we want to know when it comes to a stop, we want to know when the radicand, underneath the radical, it's a radicand, right? Is that the name for it? Radicand, right? Underneath the radical is equal to 0. So what are you solving for 0? You're solving 3t squared minus 3 squared plus 2t minus 2 squared equals what? 0. Anybody have a good way to solve that, or how did you go about solving that? Yeah?
A squared plus b squared is equal to 0, then a and b both have to be equal to 0.
If a squared plus b squared is equal to 0, both a and b have to be 0. That is correct, because anything squared is either going to be positive or 0. So both of them have to be 0. So you can solve one of them and see if the other one is potentially going to also be that. Which one's nicer? Which one do you want to start with? It's like, you know that 2t minus 2 has to be what? 0. So t has to be what? 1. Does that make that 0 right there? Does it make it 0? Yes. So is there a time when it comes to a stop? Time equals 1. Are there any other times when it's a stop? No. Is the particle ever moving straight up or straight down? So how do you figure that out? Well, what is dx dt in this case? It's the horizontal rate of change. And we know that dx dt is what in this case? 3t squared minus 3. And dy dt is what? Okay, I can continue talking to myself. It's okay. 2t minus 2. So if a particle is moving straight up when what is true? A particle is moving straight up when what is true? It's up or down, yeah. Izzy?
The derivative of dx dt is 0?
No, not the derivative of dx dt.
Oh,
Like,
dx
if dx dt is 0 and dy dt is
not
0. Exactly, right. So here's the thing. What's the only thing? Well, actually, no, there is a time here. So what do we know here? So dx dt equals 0 and what is true? At what times? When t equals what? 1 or negative 1, right? But when you plug those two values into there, dy dt when t is equal to 1, what do you get? 0. So we already know that at time equals 1 is the particle moving? No. But what is dy dt when t is equal to negative 1? Negative what? What is it? Negative what? 4. Negative 4. So at time equals negative 1, the particle is moving straight what? Straight down. It's moving straight down. For that instant, it's moving straight down. Okay. So then we do it in the other direction. So we can say at time equals negative 1, the particle is moving what? Straight down. So now let's do it the other direction. Dy dt equals 0 when what is true? When t is equal to what? 1. But what happens, that's the only time, what happens when you plug that into dx dt? It's 0.
So there isn't a time.
Yeah, so dx dt at t equals 1 is 0. So the particle is never what? Never moving just left or right. Are we okay so far?
Yeah.
We're okay so far? So part C here asks us, is the particle ever moving straight horizontal? Oh, did we already just do that? Oh, I'm sorry. Oh, great. Okay, yay. We're done. Does that make sense? We have two different ways of finding a second derivative. Do you remember that from yesterday? What was the first way that's relatively straightforward but not always nice to do? What's the first way? What's the first way to find a second derivative? What can we do, Kevin?
You can route the Cartesian equation.
Yeah, you could unparameterize it and write the Cartesian and then take the derivative twice, right? You could do that, right? You could do that. Is that sometimes fraught with potential pitfalls, like nasty, either algebraic nastiness or things that create problems? Yes. So yesterday I also gave you this right, where, not yesterday, last week. I think it's right here, right? So we do this. I would like to do this instead so we can avoid some of those pitfalls. So what's the first thing we need to find? What's that? Find what? We need dy dx first. Remember, you got to do these inside out. We need this first right here. So how do we find dy dx? What is dy dx equal to? Dy dt over what? Dx dt. You know that. We wrote equations of lines, like that's how we found the slope of lines, dy dx. So what is dy dt? What is dy dt? So we have 2t over what? 3t squared plus 1. Now what do we do to that? We do what? We do the derivative with respect to what? To t. And what do we need to use to do that? What differentiation rule? What? Speak so humans can hear you. What? Say it louder. Louder. So we have 3t plus 1.
3t squared plus 1.
3t squared. Thank you. So that is, oh, and are we done yet? No. What do we need to do? What do we have? What is dx dt? What is dx dt?
The derivative of that.
Yeah, so 3t plus what? Come on, what is dx dt? 1. Thank you. So what's our answer going to be? So our second derivative, therefore our second derivative, like this, is going to be 2 times 3t squared plus 1 minus 12t squared all over what? 3t squared plus 1 what? Cubed. Exactly. So there's our second derivative. Excellent. What's it ask us next? Is the curve concave up or down at t equals 1? So what do you now do? Plug it in. You're just evaluating d, I could almost write it correctly. What do we have? D like this. Evaluated at what? T equals 1. So what do you end up with? 2 times 4 minus 12 over 64, right? Is that correct? Which is what? Negative 4 over 64, which is less than 0. So it's going to be concave what? Concave down. Exactly. Writing a function. What's the other way? Parametric. So you have x equals x of t, and you have y is equal to y of t, and you're going from time equals a to b. Do you remember what the formula is there? Do you remember? Tanmay.
Integral t equals a to b.
Yep.
Square root of
Yep.
dy over d.
Yeah.
Dx over dt squared.
Yep.
Dy over dt squared.
Mm-hmm.
dt.
Correct. Those are the two arc length formulas. You're just going to be using those arc length formulas. So literally it's take a derivative, square some stuff, and run a derivative. The work generally is going to be, if I ask you to evaluate that, you're going to have to do some work to evaluate that. Because quite frequently, can you end up with integrals that are not really straightforward? Yes. You can end up with things that are not straightforward. But that's what these sections are for. What was 4.8? What's the topic for 4.8? We just did it. What is it? So it's parametric. What's 7.2?
Integration by
Parts. And this was what?
the fraction.
It's PFDs and trig. Trig sub. So the question is, which one do you want to focus on right now first? Which section do you want to do some practice problems from?
7.3.
When is it?
Friday.
Friday. Test is Friday. Woohoo! Woohoo! Hangashing. At sine cube theta is equal to sine of theta times what? Sine squared theta. But what is sine squared theta? Oh, is it frozen? Thank you. Sorry. So what is that? It's sine theta times 1 minus cosine squared theta. So what is that? Sine theta minus sine theta cosine squared theta. And what's the point of doing that? Yes. So now, when you have this written out, you are able to integrate this piecewise. You can integrate these two things. Like, what's the integral of sine? Right here, this, right here. And then how do you integrate this right here? Substitution works on that one. Substitution does work. This is a lot of work. This is absolutely a lot of work. Do you understand the general thematics of how this is supposed to go? I would agree this would be a very hard one because here's the thing. If you don't see this, like if you don't see that bridge right there, this is kind of a showstopper. It can be a big showstopper. It can be a big showstopper. On a test, I might give you something like, show that this is equal to this. And if you got this far, that would be awesome. Because if you don't see that, like is this relatively straightforward to understand? Sure. But how many different little steps like that are out there? Well, I can substitute that in. Basically, always remember our core identity being sine squared plus cosine squared is 1. 1. So you divide by cosine squared, and what do you end up with? 1 plus sine squared over cosine squared is equal to 1 over cosine squared. And then if you divide by sine squared, what do you get? Cosine squared over sine squared plus 1 is equal to 1 over sine squared. So that's 1 plus, what is sine over cosine squared? Tangent squared theta equals secant squared theta. And what's this one? cotangent squared theta plus 1 is equal to cosecant squared theta. So that's how I remember them. I do that tons. So how about we do one more, and I would like you to do now, let's do this one right here. Let's do this one. Which is pi over 4, right, of secant squared theta all over the square root of tangent squared theta plus what? D theta. So what do you end up with? What is tangent squared plus 1? 0 to pi over 4. That's a terrible pi over 4. I'm going to clean that up. So it's secant squared over what? Secant, right? So what do you end up with? Secant, not squared, just secant. Secant theta d theta. So what is secant? What's another way to write secant? 1 over cosine theta. So if you wanted to do this, 0 to pi over 4. So you have to integrate secant, right? That's the challenge. You have to integrate secant at this point. So you're actually integrating this right here. And this is where it gets more challenging.